networks have existed for quite some time now. Convolutional neural networks and recurrent neural networks had been reigning supreme, but things took quite an eventful turn once transformers were introduced in the year 2017. And since then, the field of AI has grown at an exponential rate, with new models, new benchmarks, new learnings coming in every single day. And only time will tell if this phenomenal idea will one day lead the way for something even bigger, a real transformer. So let's talk about what transformers are. Transformers are essentially neural networks. Neural networks that specialize in learning context from the data. But what makes them special is the presence of mechanisms that eliminate the need for labeled datasets and convolution or recurrence in the network. The two mechanisms that are truly the force behind the transformers are attention weighting and feed-forward networks. Attention weighting is a technique by which the model learns which part of the incoming sequence needs to be focused on. Think of it as the Eye of Sauron, scanning everything at all times and throwing light on the parts that are relevant. In the context of transformers, feed-forward networks are essentially a regular multilayer perceptron acting on a batch of independent data vectors. Combined with attention, it produces the correct position-dimension combination. So without further ado, let's dive into how attention weighting and feed-forward networks make transformers so powerful. This discussion is based on Professor Tom Ye's wonderful AI by Hand series on transformers on LinkedIn and Dr. Srijani Day's post on Towards Data Science called Deep Dive into Transformers by Hand. So here we go. As we've already seen, the key ideas are attention weighting and feed-forward networks. Keep those in mind and suppose that we're given 5 input features from a previous block. That's the 3x5 matrix here, where x1, x2, x3, x4, and x5 are the features, and each one of the 3 rows denote the characteristics respectively. The first step in the process is to obtain the attention weight matrix A. This is the part where the self-attention mechanism comes to play. What it is trying to do is find the most relevant parts in this input sequence. We do it by feeding the input features into the query key or QK module. For simplicity, the details of the QK module are not included here. Once we have the attention weight matrix, that's the 5x5 matrix here shown in yellow, we multiply the input features in the 3x5 matrix with it to obtain the attention-weighted features Z. The important part here is that the features are combined based on their positions, P1, P2, and P3, that is, horizontally. To break it down further, consider this calculation performed row-wise like this. P1 is multiplied with A1 into Z1, and that's position 1, 1. In other words, we multiply X1 times A1, which is 5 times 1, and add to that x2 times a1, which is 6 times 1. Everything else in row P1 evaluates to 0, so we get 11. It seems a little tedious in the beginning, but follow the multiplication row-wise and the result should be pretty straightforward. The cool thing is the way our attention weight matrix A is arranged. The new features Z turn out to be combinations of X. Why is that? Well, look at the positions of the zeros and the ones in matrix A. The next step is to feed the attention-weighted features into the feed-forward neural network. However, the difference here lies in combining the values across dimensions, as opposed to positions in the previous step. Like this. P1, 1 multiplied by Z1, 1 plus P2, 1, 2 multiplied by Z1 but 2, 1 plus P3, 1, 3 multiplied by Z1, 3, 1 plus B is 11, where B is the bias. So in the end, we end up with values like this. What this does is that it looks at the data from the other direction. In the attention step, we combined our input on the basis of the original features to obtain new features. In this FFN step, we consider their characteristics. That is, we combine features vertically into our new matrix, this one here. Once again, element-wise row operations to the rescue. Notice that here the number of dimensions of the new matrix is increased to 4. Next is our favorite step, ReLU, where the negative values obtained in the previous matrix are returned as 0 and the positive values remain unchanged. Finally, we pass it through the second layer, where the dimensionality of the resultant matrix is reduced from 4 back to 3. The output here is ready to be fed to the next block, and very similar to the original matrix really, and the entire process is repeated from the beginning. Alright, so the two key things to remember here are that the attention layer combines across positions, that's horizontally, and the feed-forward layer combines across dimensions, which is vertically. And that's the secret sauce behind the power of the transformers, the ability to analyze data from different directions. So to summarize these ideas above, here are the key points. The transformer architecture can be perceived as a combination of the attention layer and the feed-forward layer. The attention layer combines the features to produce a new feature. For example, think of combining two robots like the Cybertruck and Optimus Prime to get a new robot called the Cybertruck Prime. The feed-forward layer combines the parts or the characteristics of the feature to produce new parts or new characteristics. For example, combine the wheels of the Tesla Cybertruck and the ion laser of Optimus Prime to produce a wheeled laser device. And there you have it. That's the principle behind transformers. Thank you for watching.